all the participants. So please do feel free to ask your queries by raising the hand so that we will unmute you and you can directly talk to the instructor, or else please post your questions in the chat session. So with that, we begin the morning session of today's module and we'll be continuing the lecture on non-thermal technology, plasma technology. Over to you, sir.
Sorry. Welcome back, and really sorry for the inconvenience. And this is the beauty of all the technologies what we use, and whether it's a non-thermal technology, thermal technology, or communication technology, and what glitch we can get, we never know. So it's actually, so far what we have done is we started with the global agri-food sector, what are the challenges faced by the global sector, and how technologies can be employed at various stages and where we can use it. And then followed by advances in new technologies, mainly on the overview of the technology and main characteristics with some of those examples where and how we can use it. And then specifically, I did not go into details of each and every technology, especially those technical features, about core mechanisms, principles, very core principles, what can be obtained at any of the standard textbook. And you all have studied food engineering, food processing, so you would have come across a lot about it. And followed by, we went through some of those operating principles, mechanisms of certain selected technologies. And one thing is really important when I'm listing out any of those examples. And in future, suppose if you are asked about any technology, what are the factors which will influence microbial inactivation of a food, of any given food? So what do you think the best way to answer, to approach that problem is just think of an example and start listing out the factors, rather than having list of intrinsic factor, extrinsic factor, temperature, time, pH. So these are there. But if you think of some example, then you'll be able to come up with a constructive answer, and then it will help in proper application. Because what we do here is we do not make technologies, we use those technologies. So that means we are more on applied side of it. So that's the most important element. Sorry. So with this, we stopped yesterday a bit with the plasma, and I'll continue with the plasma and followed by some of the mechanisms. And yesterday when we were covering plasma, and I was showing you one of the video which was with the bread, how plasma can decontaminate the air surrounding that particular bread, so that we can avoid cross contamination where different applications. So I'll just show you another example how we scaled up a technology from starting from the basics. So if you look at this particular small system in the black color, this is a plasma air system which can operate with the 6-volt battery. And there's a small fan here. We created one chamber which we used it obviously for initially for bread experiment to show how we can decontaminate the air surrounding it. And then the subsequently experiments was, the main focus was mainly on meat. That's why you can see some of the meat over here. And we also carried out some of the work on strawberries and other fruits, where we carried out this plasma in uncontrolled manner. In the sense with this small fan, what you get in most of those laptops and even the computer, and with this small plasma device, we carried out with the normal air and plasma air, and we carried out the study to see what are the best parameter, how we can control this. And the next stage related to that was to carry out that study on simple total viable counts, and simple viable count, and to see after 5 hours of plasma treatment and 72 hours of plasma treatment, what are the changes can occur. And what we found, there was no colonies found in both control, neither in plasma treatment. That was a major issue. Why? Because when we do carry out this experiment in laboratory conditions, we use very sterile conditions, so that there is no cross contamination. So in order to do that, we have to infuse some of the microbial load inside the material. And I'm not going into all the stages of the data, and some of the data I presented it yesterday. And then we designed this type of particular box. And if you see this box here, this is a 1 meter cube of volume of system, which was having a refrigerated system here. That means just the cold air which is circulated around. I'll show you another figure. Yeah. If you see, these are the 3 vents on top and 3 vents at the bottom. This is a prototype of what is exactly used in cold or refrigerated conditions. So that means cold air is coming in from here and goes into this particular chamber. It's chilled and is thrown back in. So it just circulates the air. So that means even any of the refrigeration system or air conditioning system, very same method is adopted. And then what happens here is the moment air goes in from this chamber, maybe suppose you bring in a fresh load of fruit, vegetable, or any of the commodity which has to be kept at 4 degree or 8 degree or any of the chill temperature. So it will have some surface microorganisms due to various factors. And then that particular microorganisms is circulated within this cold air. And if we have this type of plasma system, as what you can see here, this is a slightly advanced version of the smaller plasma device. The smaller plasma device is a patented system which was built by one of the company who is supplying across almost most of the airports for deodorization and for decontamination as well. And this works on a simple principle. Very low voltage comes in here, and whatever air comes in contact with these 2 rods, it forms ions. So in that process, what happens is when air comes through this contact, and whatever it is having, it is decontaminated and is thrown back into the system. And then we went slightly advanced on this particular box. We also had a provision to have UV LED light system in case if you want to use UV light to decontaminate this particular chamber, and a data logger which can record the amount of plasma going in, and it can be controlled remotely. Plus another advanced version of scaled up version of this prototype is going on with having sensors inside. That particular optical sensor is based on to monitor the microbial load within a given chamber. How that operates basically is it's having very sensitive optical sensors and having a pre-made media plate. It sucks the air, throws that air onto that media, and early warning system, the moment microorganism starts growing onto a media plate, it detects the changes and it relates with the system which is already configured. The type of bacteria will grow on a specific media, and that can control the plasma device. So that was the automation part of this particular system. And inside of this chamber, as you can see, normal all the food refrigeration or food storage system had these vertical blinds, and we placed a meat sample over here, and at the bottom these are the Petri plates, what you can see, to record the microbial counts. So this clearly shows, first we investigated plasma air. What are the characterization of that air, which we'll see in next couple of slides about the mechanism of it, followed by their microbial inactivation profile. Since we made only one particular device like this, and it was quite expensive to build this, and covering all the regulations, leaks and everything. So, and then to carry out the microbial analysis at different time points. And this particular was a solution for refrigerated system. And with no surprise, this particular system was found very effective against COVID virus as well. Not exactly the COVID virus, but as to decontaminate or to degrade those viruses. And it was tested with the with some of those defense agencies in the mid 2020s. So that's the way it was. System was built, and it clearly shows how we can scale up the technology. Now, this is what all about the plasma air, hot air plasma, cold air plasma, and similar mechanism is also applied to ozone. Now, if you see the another type of this plasma system over here, which is again a very crude system, which was made as high voltage electric discharge. And as you can see here, there is a sample over here. This is basically a microalgae, and plasma was used to degrade those microalgal cells so that extraction can be carried out. This was carried out with our colleague in Croatia. They do make very high voltage discharge. So in nutshell, the plasma is any fourth state of matter, whether you break the gases with very high voltage, with microwave, or with heat. That's the way plasma is created. Now, coming back to the fun part of it is mechanism of action. So one thing is, you have created the plasma air, you decontaminated the product, you showed there's a microbial inactivation, but we have to understand what is the science behind it. Although the science is quite complicated when it comes to plasma. So even, for example, if you take high voltage, we use different type of gases, that is air. And one thing you have to make sure that when you're using plasma system with normal atmospheric air, now today it's raining, so humidity may be 99% or maybe 98% or relatively 100%. So in that condition, you may have higher moisture in the air, so you may have more production of OH radicals. Whereas when you use a dry air, you may have a completely different gas profile, irrespective of the voltage what we use. So whether it's 10 kV, 120 kV, that becomes completely irrelevant there. So basically, when you use different air, and the plasma, which contains highly reactive species, was reactive species were detected by using optical absorption spectroscopy. And here, as you can see, this is light source, and whatever plasma gas was coming out from cold plasma, that was electric source, and other one, which is hot plasma, which generates the plasma with temperature of nearly about 160 to 180 degrees Celsius. Specifically, this particular plasma system was purchased because we thought to drive this hot air plasma directly into the spray dryer, mainly for drying of, to include plasma, hot air plasma air, for drying of food ingredients, especially milk powders and other protein powders, so that we can inactivate the spores as well as microorganisms related to that. And this is small glass vessel that is cooling system to cool down this hot air plasma, because most of the food application for the plasma are always at ambient temperature or at very low temperature. So this was the simple experimental setup. The condition was made in a black box, and then optical absorption spectroscopy was employed. And then with the NIST library, we identified what are the reactive species. This was the one way with the air. Other one was when this plasma air was pumped into the liquid, into water. That's basically, we call it water treatment. And different reactive species were characterized by using wet chemical calorimetric method. That's the grease mechanism, and different spectroscopic method to measure nitrates, nitrites, and hydrogen peroxide. And also characterized by using Raman spectroscopy to see what are the different reactive species. So if we do have the characterization of the air or the water, and subsequent analysis is carried out, then it becomes easier for us to further scale it up, and it shows the practical utility of the experimental carried out. It is not we have a plasma system, just put a product and show it is decreasing. So that means that data is only applicable to the machine what you have. And if you're trying to go for publication of such work, and it may not pass through the peer review process. Now, if you look at the data here, H2O2, like cold plasma and 20 kV and 40 kV, and hot plasma, there's no other parameter we play around, because this is a commercial system which is used by a lot of surface engineering group and for modification of surfaces. And what we see is treatment of plasma in air. Within 5 minutes, we see certain level of concentration of hydrogen peroxide, and then for 10 minutes and 20 minutes. So it is not that if you have plasma activated water for 20 minutes, you'll have higher species. And if you have if you have a lower time, it will have different species. So as you can see, these graphs, like nitrates, nitrites, they all are having different profile for depending upon the treatment. The obvious reason between these two is if we try to see the correlation thing between all these three species, these all are transient species, and moreover, a lot of nitrates are converted to nitrites and nitrites to nitrate, and it's a dynamic process. So I'll show you the other spectroscopic tool, how the plasma behaves. And then when these reactive species are there, we also tested out different parameters for different time point related to pH. As you can see, the pH for non-treated ones was relatively close to 6 or so. That means it's close to neutral deionized water, slightly acidic but still neutral. And the moment we employ plasma even for 5 minutes, you can see there is a decrease in a pH of the water. Why there is a decrease in pH of the water is just because the formation of hydrogen peroxide or nitrates and nitrites, and they can reduce the pH. And that could be one of the additional side mechanism of causing microbial inactivation. So water is basically acidified. That means 5 minutes, a different treatment point when it was carried out, and when you store it for up to 24 hours, you can see there is a decrease in, that means reactive species are retained in that particular water. Conductivity and oxidation reduction potential, these all are some of the parameters. This was just done to characterize, is there any change in all these water properties when it was used for cold plasma using electric source. And similarly, similar thing was found also for hot plasma. So irrespective of the source of generating the plasma gases were having different reactive species. So as you can see again here, plasma activated water for 1 minute, 3 minutes, or 5 minutes. Immediately after the treatment for 3 different times, we had a decrease in significant decrease in pH compared to non-treated ones. And then it continued for almost up to 30 minutes without that. So that means the pH is decreased and conductivity is not, it changes, but what is the main reason behind that is just because of all reactive species. So we did not go further deeper into this. It's just because that was not the main intention when it comes to applied technologies, because we keep focus on just to understand the mechanism and what is related to the processing. Further, if we need to do further analysis with EPS, electron spin resonance spectroscopy, and identification of ions and all those dynamic chemistry, that can also be easily carried out. Now, if you see the mechanism again here, so basically, if you see the gas phase, I'll start with bit by bit. If you see the gas phase, with the plasma, we have ozone, NO, OH, O radicals, N radicals, and numerous other combinations. And when it comes to in a liquid phase, we also have again reactive oxygen species, reactive nitrogen species, and all these species, they impact the cells. So this is a simple schematic of a plasma device with having oscilloscope to measure different reactive species and plasma plumule, and a light source goes on to this to measure what are the species coming in. And this is the pin system, which is open pin system for treatment. And this is the jet system. And all these are only the applicator. The main component of this is mainly a plasma source. Now, if you look at this particular reactions over here, this is optical absorption spectroscopy, and compared with the standard libraries, and we see there are a lot of different reactive species are formed with respect to different wavelengths. So this was just the characterization. And when we look into different reactions, obviously, because of free energy, we can see a lot of different types of reactions are formed and different reactive species. Now, if you look at this particular diagram with the gas and a sample which is treated with the plasma. When plasma is on, you see that the way reactive species are formed. These are all was a high-end technique was used to characterize that. And to be honest, this was carried out with our electrical engineering colleagues. And then when plasma was switched off, and we see much more distribution of those species around it. So it is quite complicated chemistry. And when we use plasma, our main focus is mainly on how we are able to kill a bacteria and what causes killing of the bacteria or insects or chemical changes. So the thumb rule here is, because of reactive species, it causes oxidation, and oxidation can happen to any of those macromolecules, micromolecules, or to microorganisms. Now, if you go to different mode of actions, when it comes to insects, reactive oxygen species toxicity is through respiratory system, which not only impacts its circulatory system, nervous system, or immune system and causes mortality. It is because, as I said the other day, we cannot become resistant to oxygen, same as insects cannot develop resistance against plasma species. Well, as of today, it has not been proven that insects can become resistant to oxygen, to the plasma species, whether it's a reactive oxygen species coming out from plasma or from insects. And when it comes to bacterial cells, is again, this is slightly complicated diagram, but it's simple stuff here is because of UV, because of reactive nitrogen species, oxygen species, and reactive hydrogen species. Depending upon the gases, free radicals, it can impact genetic material. It can lead to degradation of outer membrane. And then once outer membrane is oxidized or degraded, and it can leach out a lot of cytoplasmic material, causing permanent death to the cells. And another application here was used when we have the reactive species, and then we want to pump in those reactive species into the specific type of cancer cells or tumor cells. We employ ultrasonics or different technique to cause a pores, and then to transfer those reactive species into those cells to have a specialized application. So this is just a simple way of different reactive species can impact protein in the cellular membrane, DNA of cellular membrane, affect cell wall, cytoplasmic membrane. Obviously, that also depends upon gram-negative and gram-positive bacteria. But these are bit on hypothetical side of it, and these conditions, changes in the protein of a bacteria or a DNA of a bacteria or a genomic sequence of a bacteria, or a phenotypic behavior or virulence factor of any microorganism, can only be studied in a pure solution. So if this particular bacteria is present on a strawberry and the strawberry is subjected to the treatment, then it may have completely different, we just see the inactivation, and we won't be able to see all these exact mechanisms. So this is a classical example here, scanning electron microscopy of Bacillus subtilis vegetative cells, simple untreated cells and treated cells. So as you can see, this is a plasma treated cell, and this was obtained from the surface of black pepper. So again, in a nutshell, reactive species bombarded onto the cells, lipid peroxidation of the membrane, that means lipid present in the cellular membrane causes oxidation. Membrane can be damaged, proteins can be damaged, and once membrane is damaged, it can leak the intercellular compound, and then oxidative damage on proteins and lipids and genetic material. And how DNA is getting oxidized is mainly because of UV light. Specific reactive species are formed with a specific wavelength, and that causes the attack on DNA. And that's the reason why we have seen it's very effective against the virus as well for DNA and RNA. And then when it comes to DNA, it is mainly related to formation of thymine dimer on a DNA. And still we are trying to establish a proper mechanism how it is happening. And believe it or not, it's slightly complicated because treatment is done on one place, extraction of DNA or working on different microorganisms, because certain microorganisms are quite resistant and gram negative, gram positive. It itself is an area of further investigation, but that goes through the fundamental sciences. Now, with this mechanism, so we know how in depth we can investigate the mechanism associated with any given technology, and you can go as deep as you want depending upon your interest. And then when it comes to make a balance between academic research and industrial research, so we have to draw a line where we want to stop ourselves. Now, if we go back to the technology so far, what we have covered about cavitation is the cavitation ultrasonics, and on a plasma. I focused entirely on these two technologies is not because these are the two active areas what we are working at the moment, but also because most of the other technologies when it comes to ozone, UV light or high pressure pulse electric field, they are very well investigated technologies, and most of these technologies are at commercial level and is being looking for regulatory approvals. Now, one thing what is really important here to see how and what is the basis of selecting the relevant technology. So I might be covering this particular slide. This is a very interesting bit once I'm finished with some of those other technologies related to ozone and bit on high pressure and different applications. Now, take any given technology, for example, high pressure or PEF, ozone, UV light or UV LED light. First and foremost is the food safety. Food safety is a prime motivator for the use of technology for application. So if you are able to achieve microbial inactivation, that's good. We are able to solve that problem. But where we are able to get that microbial reduction, it's a model solution. Whether it's a conventional technologies or novel technologies, all these technologies can achieve over 5-log reduction. You've already seen in previous yesterday's on plasma side, we showed the model food solutions or even ultrasonics or infant milk formula or fruit juices was able to get up to more than 5-log reductions. And then when it comes to liquid food, and one thing is majority of non-thermal technologies, they are very well applicable to liquid food. For example, when it comes to high pressure processing, we can use it for fruit juices very well. For meat or fresh produce, it can be used, but it will cook the product, but still will not be able to get very high level of microbial reduction. Pulse electric field again is very good for liquid food applications for achieving microbial inactivation, but for solid food, it can do some of the inactivation, but it can also be used for other applications. For example, improving pulse electric field treatment followed by freezing the product. It have a better texture and better freeze drying properties. Similar thing applies for high pressure processing. And other application for high pressure itself is even if we want to remove if we give a high pressure treatment of 100 megapascals or 150 or 200 megapascal treatment to crabs, it is very easy to recover meat out of it because it helps in detachment of shells from the protein. So there are different applications, and day by day, a lot of different researchers around the world are investigating new and new applications for each and every thing. And majority of these applications are coming in based on simple logic. That means what it does and what we need. So if we have a proper combination of these two, we can look for application. Same thing for ozone applications as well as ultrasonics. Ultrasonic is really very versatile one. It can be used for range of different applications. Similarly, it's for light based, whether it's UV light, pulsed UV light, white light, or IR light, like different types of light-based technologies, they all are able to get up to 5 log reductions when it comes to liquid food. Now, the problem starts when we are looking for solid food. Over here, the issue is in majority of the cases when microbial load is there on these surfaces, we can only decontaminate the surface, and uniform treatment of these samples are quite challenging. For example, if you take this particular salmon fillet, and if you are exposing it to dipping into ozone containing water, that's perfectly fine. It will be able to clean whatever it can expose, but this surface is not very smooth. So it has to have a mechanism where it can go into the grooves or of this particular product. Same thing applies for broccoli or strawberries, whereas when it comes to tomatoes and apple, it's very easy to easy to get rid of microorganisms even by simple washing, because they have a very smooth surface texture. So majority of technology, they can get 1 to 2 log reduction. So that means we can get up to 90 to 95 reduction. And that is even a good number, because even if you look into the literature, when we use chlorine for washing, max to max what we get 1 log or 2 log without compromising the quality of the solid food. Now, this is one thing which is need to be considered. And now if you're able to achieve microbial inactivation, then we see whether we are able to integrate into the process line. For example, if you have a fresh produce, tomatoes, and you want to introduce and to use high pressure processing for inactivation, and or you want to use cold plasma for cleaning, washing, surface decontamination of tomatoes, are you able to integrate into the process line? So that is called technology transition, because every process line, every industrial line is different. So it has to be investigated how it can be integrated into process line, and then to look into the process efficiency, whether you're improving process efficiency, cost of the production, and cost of employing that technology, occupational health and safety. For example, if you want to use ozone for washing of fruits and vegetable or a plasma, so there are also occupational health and safety, because as I said, it contains reactive species, although they are short-lived, but still those health and safety is to be determined. And these are some of the limiting factor why these technologies are still under consideration by novel food, coming under novel food regulation. Now, if it's not able to achieve microbial inactivation, then it's not suitable. So end of story. And if it is able to achieve, not able to achieve microbial inactivation, then you may have to come back with the combination of these technologies. And then if you're able to do that with the thermal or existing technology, then we look for commercial validation. So that is the way how we increase the TRL levels. Now, as I mentioned, we are going to cover some bit about risk assessment and how these technologies can be integrated into the process line. Now, imagine if your raw material is having 2 log of population and your 5 log of population, and your technology is able to achieve 5 log, and there are certain bacteria which are left, whether it's pathogenic bacteria or spoilage bacteria, because majority of the food regulations says, if you look either FSSAI, Food Safety Standards Agency of India, FDA or EU, any of those regulations, it says any given time you should not have microbial load more than 0.5 log or 200 CFU per ml. But imagine if certain bacteria which are given those treatment and they are left over in it, and then they can cause further growth of microorganisms, that's perfectly fine, but still within the limit. It will not cause a death or it will not create a problem. But it can induce one problem, that is antimicrobial resistance. So next couple of slides we're going to talk about is now the validation of technologies when it comes to microbial load is going towards measuring genomic sequencing. Very simple, latest example here itself we have is about the COVID. First, we test the COVID, that somebody is having COVID or not. Then we go for genomic sequence to see what type of virus it is. Similar thing also applies when it comes to microorganism, where food is at the moment is untouched, but soon it will be coming in, because a lot of work has been carried out and a lot of discussions are already going on with the microbial risk assessors to see how best we identify what is the risk of antimicrobial resistance and how we can mitigate that, because we never know whether those bacteria or these foodborne pathogens are may be able to get their resistance or inactivation, or sorry, get resistance against this technology. So if we go back to the risk assessment and novel technologies, so first thing, what are the causes of antimicrobial resistance in a food chain? It's a primary production, food industry, and household. If you look at this particular performer here, farmers, usage of antibiotics and different sanitizers. We are using a lot of sanitizer as a result of COVID, but that is one thing is quite an issue, that we might have some bit of resistance coming in microorganisms because of excessive use of sanitizers as well, or indiscriminate use of sanitizers at agriculture farm, aquaculture facilities, or animal husbandry. And antimicrobial like antibiotics, pesticides, sanitizers, and disinfectant. So this is one of the cause of antimicrobial resistance at farm level. We all know that a lot of pesticides are used on different crops, as well as different disinfectant. When it comes to food industry, again, food handlers, lot of sanitizers, whether it's a chlorine or peracetic acid or different chemicals, or antibiotics. Other biocides, that is surface active compounds, iodine oxidizing agents, acid ionics, and others, a lot of different chemicals, or decontamination processing treatment, as we have seen a lot of non-thermal technologies over here. And then again, preservatives, which are used in different food products. This is a generic overview. And last one is household, that is consumers, again, antibiotics, sanitizers, raw produce, and any of those produce. So there are numerous causes, numerous elements which can cause antimicrobial resistance in a food chain. So when we are replacing existing processes or existing technique which are used for microbial inactivation, we have to consider what are the causes. So there's no point in or changing chlorine in food processing environment, but whereas the same chlorine is used in a farm level. So the crux of the problem is we have to look everything from farm to fork as a chain. So it's not, there's no point in solving a problem at a stage where things are already being spoiled. So that's the main point I would like to convey here. Now, when it comes to risk assessment, so basically this is now today, if we're going through some of those regulatory text and regulations about EU, another one, it is, to be honest, very dry topic, and it is what it is. So you may start hating me like about saying that's just too much of text about regulation, but it is important to know those particular strategies. How do we carry out risk assessment? How do we do validate a technology? Validation is not just the process validation on the processing side, but also the validation before it is used in industrial setting. So what is basically a risk assessment? Risk assessment is simply a process to scientifically evaluate the probability of occurrence and severity or potential adverse health effect which may cause because of result in due to foodborne hazard when it comes to food. So risk assessment is also done for any given process. When we work in a lab, every researcher has to carry out the risk assessment of the process what they're going to employ. So in risk assessment, there are three main important things. One is risk assessment, which is science-based. That means you identify hazard and look into dose response assessment and exposure assessment. For example, if you're using ozone in food processing environment, so what are the hazard? Hazard is ozone gas itself and the person operating it. Then we need to know what is the dose which will cause human toxicity, or what is the exposure level. That means if it is a person is exposed, how we have a corrective action to that one. For example, if ozone is used in a water solution, its half-life is around 21 minutes. And if you're generating ozone at a given location and in open air and within 2 to 3 meters, you will not be able to smell that ozone because it will just completely disappear. Or how do we control that? So these are the three important things: risk assessment, which is science-based, and then risk management, which is mainly a policy-based. That means what are the control decisions, determining the acceptable risk and controlling alternative. So this is for risk management, and then everything related to risk communication. It's very simple. It's actually a lot of you might be flying through airport, and it is said like you should not have a liquid more than 100 ml. So that does not mean if we have 100 ml will not have, if we carry 100 ml will not have a risk of any of those harmful chemical or explosives to be carried away, to carry to the plane, but it reduces the risk. So that's what it is. How we can reduce the risk. We cannot make a zero risk. So the same principle applies over here when we talk about new technologies or any other food processes. So risk assessment, knowledge, that is risk question, hazard, product and matrix, population group, exposure scenario, what is model structure, data collection, background knowledge. So that risk assessment is a revolving process for any given technology. That is one of the main reasons why certain technologies are still not used in, are not allowed to use commercially. For example, high pressure is allowed to use commercially if your objective is not to prove that it will improve the food safety profile. That's what is the European Food Safety Agency or Food Safety Authority of Ireland they come up with. If you say you're using high pressure to improve the process efficiency, that's perfectly fine. But if a product is having a thermal process which is already approved and which is known method for microbial inactivation, that's perfectly fine. And then when we have a knowledge, we process, we do different types of modeling, transform and visualization. An application improves understanding, predict risk, and assessment of different interventions. So take an example here about exposure assessment of Salmonella species in chicken. So when we were covering about different technologies for processing of chicken and all, that's only very small part of full risk assessment. So if you see growth, where all Salmonella can grow, retail storage, transportation to storage to home, or storage at home. So this is what I meant. If we have, if we reduce the Salmonella by 2 log in a chicken, so still it contains even 0.1 log or 0.2 log, but it can still grow depending upon what place it has been stored, preparation or cross-contamination, cooking, consumption, and a dose. So this is risk, cross-contamination, risk with the consumption. So these are the way how the exposure assessment models are carried out, and then different simulation studies are carried out. So that's goes all for risk assessment. Majority of risk assessment for specific bacteria or microorganisms like E. coli in E. coli in fruit juices, Salmonella or Campylobacter in chicken, this is being carried out, but not with reference to novel technologies, but as a reference to handling and consumption and processing and storage. So similar approach has to be carried out when it comes to novel technologies. So over here, what are the hazards? What can go wrong? What are the potential consequences? How likely is it to happen? Is the risk tolerable? That means key element of microbial risk assessment that includes hazard identification, exposure assessment, hazard characterization, dose response relative, severity assessment, and risk characterization. So these are the key elements what I already discussed previously. And as I said, there are a lot of microbial risk assessments are already available on with WHO or FAO. That is Listeria monocytogenes, Salmonella in eggs as well as in chickens, Campylobacter, Vibrio in fish and shellfish, and E. coli in beef, and also in a fresh produce. These are already available, but not with reference to new technology. If a new technology is introduced commercially, the risk assessment has to be included into this risk assessment. That will be mainly based on frequency of contamination of food, number of microorganisms when contaminated, growth before consumption, frequency of consumption, amount of food to be consumed, and number of microorganisms consumed with each serving. So all these are a part of novel technologies. And whatever area of research you are involved in, this part of the work has to be carried out by specialists who are very good in risk assessment, modeling, and simulation, and have a microbiological knowledge. So one person cannot do everything. That's why we come up with a package. If somebody want to use high pressure in the industry, it is not just to install an equipment over there and start using it. There are a lot of things has to go around it to develop SOPs, develop the risk assessment, what can go wrong, and what will be the consequences, how we can address those. Now, again, coming back with this different risk assessment framework. Now, as I go further up, it will be having a lot of different flow charts, and most of these are taken from different references. And this is the exact presentation which I carried out in Russia on WHO and FAO antimicrobial resistance with the new technologies risk assessment framework. So these are some of the work which is in progress, and soon, maybe by next year end, there will be risk assessment will be introduced for new technologies as well. So here again, hazard identification, selection, combination of food, animal species, focus mainly on meat, because meat is a very risky food product. Most resistant bacteria, exposure assessment at different stages, whether it's a pre-slaughter, post-slaughter, at resistance at retail level, and then again how we carry out. This include again hazard characterization is very similar what I already mentioned. Risk characterization, that means ranking of the combination of the risks, and risk management options. So how we can carry out. And then again, if you look into this particular framework, hazard identification. Now, when it comes to antimicrobial resistance, you have to profile those genes, antimicrobial resistant genes. If you remember, when we're talking about microorganisms which are inactivated, but still they are alive. So that means DNA and RNA is already out there. So that means their genes are already available, and which can cause a virulence factor, and they can grow, and they have ability to be transmitted to a half-killed bacteria, and that's the way resistance can develop, and it will continue. That's why, even though E. coli was discovered almost more than 100 years ago, but still it is classified as emerging pathogens. It's not emerged today, but because they keep revolving. That's the reason we call it as an emerging technology. Even high pressure still is classified as emerging technologies, because that technology emerged while ago, before almost 50 to 60 years ago, but still it is classified as an emerging technologies. So when it comes to exposure assessment, so where all we can get exposed to in farm, processing, retail, food preparation and consumption, and then how do we characterize it? So in a simple way, you take a technology, we identify different hazards, what it can cause. We look into exposure assessment. That means what all and where all it can expose. For example, if you have tomato, you got it from the farm, it's having surface microorganism. You dip it into ozone containing water or plasma containing water. You clean the tomatoes, it's left over with some of the microorganisms. And then when you look at the characterization part of it, the wastewater, whatever is left after the tomato is washed with plasma containing water, ozone containing water, and that particular water is thrown into the drain, and that drain contains some killed bacteria, half killed bacteria, and those DNA or RNA or so, and then it goes in back to the field, and then that particular water is used for growing crops, and then again we are transferring the bacteria. So there are a lot of chains which causes antimicrobial resistance. And I need not to go further deeper into this, because one of the latest example, you all know about COVID virus, from where it came in, how it happened, a lot of theories around it. But again, the same thing happens when it comes to the food or microorganisms. So that is the framework of risk assessment. And believe it or not, I really personally don't like this area, because it's really too much of ifs and buts. Now, when it comes to cross resistance between biocides and clinically relevant antibiotics, microbial species, E. coli, Pseudomonas, Bacillus, E. coli, Campylobacter jejunum, Salmonella enterica. Now, all these biocidals, different chemicals, how they have been used, and because of having the resistance against these antibiotics, which are used at different levels, or biocidal compounds, so these are restricted for use in not only food but also for generic purpose, and these are the ones which are developing a lot of antimicrobial resistance. Now, with this, if we try to see our risk assessment associated with cold plasma. Now, what are the potential risk factors associated with cold plasma? And the same thing exactly can be applied for any given technology. So one of the very interesting element, if you are doing your PhD on a specific technology, it is good to have one of those risk assessment frameworks which are already well established on WHO or FAO website. Why I'm referring to WHO and FAO framework, because that is universally accepted. EFSA is having their own way of risk assessment. FDA is having their own way of risk assessment. FSSAI may have their own. So there are different agencies: Australian, South African, Chinese Food Standards Agency, UK Food Standards Agency. They have their own frameworks. But easiest one, when I say easiest one, is easy to obtain the information, is from FAO or WHO. And it is very interesting to see how you can develop the risk assessment with your own technology, what you're working on. For example, over here, when it comes to cold plasma, potential risk factor using cold plasma, one is electric charge system. We're dealing with very high voltage. So what damages it can cause? So how you are going to operate it? Thermal damage, formation of UV radiation on a product surface during treatment, or formation of UV radiation, it may expose you. If you work with UV light, you have to have some of the safety glasses. So these are the risk assessment for the person who is operating the equipment. At the same time, the person who is going to consume a product which is treated with the new technology. There are two different elements here. Now, as far as plasma is concerned, there is no evidence at the moment or undesirable side effect of plasma treatment, because this is also used in the medical industry. But in short term, it may have cytotoxic effect, or long term may have mutagenic effect. So some of the research, if you see some of those risk assessment related to this, involves assessing possible human, environmental, and societal risk of novel technologies at various stages of the developmental process. That means the risk, what it can cause to humans who is using a technology or going to use the product, if it is treated with the technology. Second, environmental risk. That means what all it can have positive or negative environmental benefits or risks. Societal risk, what risk it might have on a society by using a specific technology. And the classical example over here is the gamma radiation itself, because gamma radiation is really a very interesting technology which can be used for almost all the type of product, and it's very simple in operation. But the problem is the consumer perception or society per se would not like to see gamma radiation, especially in Ireland and most of the European countries. They do not like to see anything related to gamma radiation. And because the way technologies are communicated, so this communication part is really important to convince a consumer also, because often consumer, they get confused between radiation and gamma, ionizing radiation and non-ionizing radiation. That's why in one of the plays, when I was presenting about ultrasonic radiation, irradiation, that's just basically a transfer. They say, oh, you are using radiation, so that is really harmful. So, whereas radiation is one of the mode of heat transfer. So the consumer perception is very, very different, and it's very difficult to convince a consumer. So it has to be communicated in a proper way. Now, coming back to this particular topic, now again, safety aspect, non-thermal plasma, electric current, UV radiation displays certain impact on cell performance. However, so far no adverse effect has been attributed. Assessment of disinfection capacity and ecotoxicity impact of atmospheric cold plasma treatments. Atmospheric plasma for non-thermal plasma exposure on in vivo toxicity effects. So these are some of the studies which are clearly shows. There are also a lot of data which is presented in the scientific literature, which shows the risk assessment related to a technology. This is exclusively on plasma. Same thing, you can also find it for high pressure and the technology. So when any of those agencies are doing a proper risk assessment on a given technology, they look into the scientific evidences, and these scientific evidences are in a peer-reviewed publication, and majority of us, including those who are listening and ourselves, we are involved in creating a data. So whatever experiments we carry out, we put it in a publication domain, and then the evidences are collected, they are pooled together, and then to see what is overall conclusion of it. I'll give you a very strange example over here. I've been part of a committee on FSAI, that is Food Safety Authority of Ireland. A lot of industry wanted to use a specific technology in food processing operation. So we carried out appraisal for a lot of different technology, and it was concluded that for high pressure, we do not have enough of scientific evidence on in literature. It was very surprising, because when we looked into high pressure for fruit juices, we could not see the convincing evidences across all the fruit juices to say that yes, this technology still can be used. So it shows that the work what is carried out goes in the scientific literature. We create a knowledge, and that knowledge is used to draw down the conclusions. And so again, coming back to the same plasma exposure, device, working gas, treatment time, input energy, whether it's repeated or continuous exposure. So these are the exposure to the plasma. Again, cell stimulation, migration, proliferation, or wound healing. These are some of those applications as well. Can it cause DNA damage or genotoxicity, mutagenicity, or toxicity related to cell, that is cytotoxicity? Cell cycle arrest, induction of cell death, and all these are related risks associated with plasma. So optimum treatment parameters should be set to minimize the risk factor. So how we have to treat it, in what way should be treated, so that we can minimize the risk factor. Mix of all these parameters are adapted individually for each application. So risk assessment is done for the equipment for use in a lab, for use in industrial settings, and it has to be carried out for each and every process what we try to employ. Further investigations regarding the nature and safety of plasma treated product is required. Now, as I just showed you some example related to plasma and how it can be used, risk assessment is required. And similarly, a lot of risk assessment has been carried out for use of high pressure and pulse electric field, but for different applications. And even if we have a best technology, best food safety profile, improved process efficiency, at the end, the consumer is the person who is going to consume a product, and it is very important to inform consumer how the product, the origin of the product, that is traceability, how it's been processed, and what technology has been employed. And that is the trickiest part, which everybody faces the problem. I'll just quote one small joke related to technology. It is quite real. It's I was in my own hometown in India, and there was a couple of uneducated, well, not uneducated, I won't say uneducated, the farmers were over there, and 5 or 10 years ago, and they were somebody was reading a newspaper, and he read, oh, our CSIR director, some scientists are going to use a nanotechnology in agriculture, and nanotechnology and biotechnology in agriculture. And then one of the person, he came up, he said, oh, nanotechnology is failed in India. It cannot be used in India. Well, he was talking in local language, and one of the fellow was very surprised. He said, you are a farmer, and what do you know about nanotechnology? Then he said, well, I've seen a Tata Nano. It can't work in villages. So he related that nanotechnology with the Tata Nano car. So the same way, gamma radiation can be linked with the radiation. So it is the consumer, convincing consumer is quite challenging, and once they develop a perception, they do develop a perception. So we do have a lot of challenges, but that does not mean we should not work on a new technologies. When there are challenges, we have to address them. So with this, I conclude this risk assessment and mechanism related to plasma, and will continue with some other technologies related to oxidation, that is ozone, and will run through those technologies because majority of the stuff is known there. And again, I'll apologize for the delay in the beginning. It was all possibly because of some rain or so, and we'll see you at 11:40, if that's okay. And meanwhile, if you have any question, feel free to type it in, and we'll be able to answer them. So welcome back. So I'll now quickly go through some of those already well-established technologies. So, and I may not be covering almost a lot of other technologies, and you're strongly advised, obviously, to, depending upon your interest, to go through those. And not much has moved on well-established technology because these are already very well investigated. However, a lot of applications, risk assessment, and further validation at industrial settings and scale-up operations are undergoing at the moment. So, looking at other oxidation techniques such as ozone and UV LED light. So, I'll have very specific examples related to that. Now, if you look into the historical perspective of ozone, like even we call it as a novel technologies, but which was discovered almost in 1839. So that means almost 150, more than 150 years ago. And ozone was started for drinking water, and even now it is also used for water treatment. It did get a GRAS status in by FDA, that is generally recognized as safe, and they did approve for as a direct additive to food in 2001. So with this, a lot of applications started in the food, but in Europe, it is still not allowed to be used. In Japan, it is used, and a lot of applications are what we go for ozone application, very similar to what we think of for plasma application. And if you use it as a processing aid, then it is okay to use rather than directly using into a food product. So as far as applications are concerned, it's again fresh fruits and vegetables, very similar to plasma. Food grains, meat and meat product. Again, there are a lot of issues when it is used with the meat, especially for oxidation of surfaces. And it can also again cause oxidation of cholesterol to convert into dehydroxy cholesterol, which may have more carcinogenic properties. Surface decontamination is possible by aqueous ozone. When we say aqueous ozone, it's ozone which is present in the water, very similar to what we have a plasma activated water, that is plasma in the water, the storage in a gaseous form and impact plasma. So original plan was to start with the ozone and then to show how we moved on to the plasma. So we won't say that we were the first group to start plasma in food, but a lot of things were working. But our genesis of moving from ozone to plasma was mainly because of some of those issues which were raised by the industry whom we were suggesting to use. So for example, if you look into the simple scenario for aqueous ozone, this is a hypothetical system which is mainly for, any fresh produce coming in for pre-wash goes in washing tank. Normally you have chlorine over here or peracetic acid dipped into it, and then you have ozone. And if the chlorine is used, there is another final reasoning option to remove the chlorine, and then it goes for packing. So still a lot of water is used, and the only advantage if we are using ozone over here is just we are not using any chemical which will leave the residue. So that was the obvious advantage of using ozone. Now when it comes to plasma, we can use plasma activated water over here, or just clean produce which is harvested goes into a packet with the plasma, as what you have seen yesterday on impact plasma system, and then it goes to consumer, and consumer does the washing and consumes. So that reduces the water usage. Now when it comes to ozone generation, and I must remind you that this is all from one of our book, and I think I have a snapshot of that book in Ozone in Food Processing. That was the first ever book which was exclusively on written on ozone, different applications, as well as on risk assessment and occupational health and safety of ozone. Now, simple way of ozone generation over here is generated by reaction of free oxygen. So if you see these two discharges, it's very similar the way you see the plasma dielectric barrier system. So oxygen system, if you purchase any ozone generator from any other company, it can cost as low as 1,000 rupees all the way up to whatever level. It's very low cost. It's just because cost has gone down compared to what it was 10 or 15 years ago for normal application. If you open that system, what you'll see is mainly there are high voltage, this one like exactly what we get for a plasma, when air goes through that, and then because of high voltage, it converts, breaks the oxygen into O, and one of the O attaches with another oxygen to make ozone. Now here in this case, if we have increase in flow rate of oxygen into it, less of ozone will produce. The reason behind that is less of the residence time will be there within this discharge. So in nutshell, ozone is generated by reaction of free oxygen radical with diatomic oxygen to form triatomic ozone molecule. So that's a simple step here. And now this is one of those classical experimental setup what we had for treatment of ozone for liquid foods. One interesting thing over here was only for delivery of ozone using in tiny bubbles. Because what was found that when we generate ozone either with oxygen tank or with the normal air, the ozone forms a bubbles, which is bubbled through a bubble column reactor. You can call it a bubble column reactor. At the bottom, the bubbles goes in, and then you can have either a water or any of the food samples, that's especially like juices for the treatment. And interestingly, when this work was carried out on apple juice, which was original approval of FDA for direct application in food for apple cider, it produced not only good microbial inactivation, but also it was a golden color orange juice, like what we normally seen. It was not that brown as what you can see enzymatic browning in normal juice, or non-enzymatic browning because of thermal effect. Whereas when we used it also for strawberry, and believe it or not, that strawberry juice was looking like an orange juice because of oxidation of anthocyanins and anthocyanins as well as the ascorbic acid. And at very high concentration levels, we were able to get rid of almost 90 to 95% of anthocyanins as well as ascorbic acid. So there, another application comes into action, how we deodorize or to degrade pesticides. How do we degrade various phenols like colorant, colored water and all, to make it much more cleaner and to act as oxidizing the organic matter. So that's so any negative feature over here can be used for another application. Another application with this, what we were investigating by using a starch solution. When a starch was given ozone treatment, and we were able to oxidize that starch, and its RVA, that is rapid viscoanalysis, on pasting properties of that starch was completely different. So that means instead of using sulfuric acid or different acid treatment to oxidize the starch, ozone is the best candidate for oxidizing the starch. And interestingly, and when we saw that it was a very limited viscosity of starch solution when subjected to ozone, obviously same thing can be achieved with the plasma. And we're talking to one of our colleagues that we could not see any of the rheological properties. Then he came up with the new interesting application, saying that that starch will be really useful for the paint industry as well as for textile industry, where they do use a starch, but they do not want to see high viscosity, especially in the paint and all. So there are different applications. If it doesn't give a positive result for A, but that positive result can be used for another application. As in the case of giving example of cavitation. Cavitation is not not a desirable phenomena when it comes to impellers, or when it comes to transportation of water from one location to another, because cavities can cause damages to the pipes and propellers. But same cavitation is used for destruction of matrices. So every application what we look into, we have to look it with an open eye so that we can investigate different applications. So now if you look at this particular case study on E. coli on a gas flow rate. So this is 0.03 liter per minute. And as you can see, if we are increasing the flow rate, the inactivation growth curve is changing, right? Whereas when we have low flow rate, or this one, and then we have a better inactivation profile. And the obvious reason here was not only the bubble size, because this gas flow rate was also controlling the ozone concentration as well as bubble size. And the bubble size, smaller the bubble, more will be the mass transfer, where the very small bubble will have very high level of ozone in it. And so these are a couple of factors which helps in determining microbial inactivation profile. And another important thing here is when the bubble size are very big, so less of mass transfer is happening. Whereas bubble size is very small, then there's excessive amount of ozone, but there is channelization, is a channel formation of channels are possible. That means all the bubbles, they form a stream and they just escape the bubble column reactor. So whereas when we have optimum bubble size, which can cause the agitation in the liquid, that makes completely different application. That means, I just go back to this reactor once again, and another application when we introduced ultrasonics within this particular chamber, that is one of the process of AOP, that is advanced oxidation process. What we found, it was very, very efficient in oxidizing the liquid, and we used that particular system for treatment of water, especially for reducing the BOD and COD of the wastewater coming out of the food industry. So that means agitation is also important, which is also controlled by type of the bubble it forms. So then it was found that MEST was related to 0.12 liter per minute, because here we had highest ozone concentration but less of agitation. Over here we had more of agitation but less of ozone in it. So that was found to be optimum, but that's optimum was only for a specific bubble column reactor and the system which was used for transferring that ozone. Similarly with the gas concentration, and this is basically ozone concentration in microgram per ml. You can take it, convert it easily into the ppm, and then how different concentration of ozone was causing microbial inactivation. And that is quite a significant number in a given time frame for achieving, and that too without the use of heat. So that is one of the important feature over here. And not very similar profile is seen when it comes to plasma activated water, although we do get a significant amount of degradation. The reason behind that is when we use plasma, we have other reactive species. So best part here is to not only to look at the plasma itself, but also to see if ozone can do the same job. There is no point in using a higher end technology. Now, another one is how do we come up with the inactivation one? We call it modeling, or you call it as a curve fitting. So if you look at this particular inactivation profile here, now over here you see there is a bit of shoulder here and then further decrease, right? And then what will be the D value? So historically, we always use the first order kinetics to get the D value, and possibly I might go on Excel file to show how we can use different type of models to predict the D value in order to avoid the I was just missing the pointer. So if you look at this particular curve over here, the green line at a 50 microgram per ml, you can see a bit of shoulder here and then further decrease, right? And this is first order kinetics, that is first order decrease in this. And if we have to calculate D value for this, 1 log reduction from 6 to 5 will be around 15 minutes. But second log was, if you take it from 5 to 4, it is only few minutes, whereas first one is showing 12 minutes. So correct D value is very important to avoid calculation of to do under processing or over processing. As you can see from this particular graph, that is reduction in log numbers subject to K and plus population time T, either today or maybe tomorrow. We'll go through the on Excel file to show how we can easily calculate and do this microbial inactivation. Now, moving, that will be carried out on Excel. So, and hopefully I'll give a basis how we can install it on your Excel, and tomorrow, or if you are present with your computer, because most of you might be listening on a phone and other thing, then you can see how best we can fit in different types of model which has been proposed by different microbiological, different mathematical modelers focusing mainly on microorganisms or microbial inactivation kinetics. So as you can see here, this is simple first order kinetics, unfiltered juice. When we had juice which was passed through 0.05 mm sieve, then we had different inactivation profile. When we had with 1 mm sieve, we had different inactivation profile. And without pulp, we had a different inactivation profile. As you can see, unfiltered, it took almost 15 minutes to get at least 5 log. Whereas when we had clear juice, we had a different inactivation profile. And what the curve, what you see over here, is mainly causing ozone demand, that is demand required to oxidize the organic matter or consumed, which is not available for microorganisms to get oxidized. So all these 3 or 4 different scenarios, they have different D values. So D value is not very specific to a technology, but also based on the organic matter present in a food. So if you use ozone for milk, for instance, will have a completely different profile. And obviously, because most of the ozone will be used to oxidize the lipids present in a milk. So whereas defatted milk is different profile, whereas skim milk have a different profile, but ozone for milk is obviously not advisable, and it's not been, there's no point in carrying out that particular operation. So if you look at here again, time required for 5 log, then combined with different pH values. So we see different inactivation profile. So when it comes to ozone for liquid food applications, and the similar thing can be investigated for fruit juices using plasma, and some of the studies has been carried out. We did not go for liquid food applications of plasma, it's just because we have already investigated a lot with the ozone, and similar thing is expected from that. Now, the conclusions from that particular ozone treatment of liquid food: 1, fast microbial inactivation can be achieved. Little resistance is possible as far as ozone is concerned, and less energy is required. Obviously, only energy required is for the production of to run the generator for ozone generation. Depending on the juice, significant effect on safety and processing parameter, and this is very, very application specific. So, as I said, if we have pesticide residues in the water, and you can see different pesticides which are used at by farmers at different on the fruit crops to avoid insects or so. And this is pesticide removal or degradation efficacy of vegetables with tap water and ozonated water. Even the tap water was able to remove some of the pesticide which is present on the surfaces. And whereas when we use ozone water, ozone containing water, we have significant increase in removal of these pesticides plus the microbial load. So that's some of the added advantage of using ozone. And one thing is, if we use ozone for tomato juice, we see decrease in phenolics, compound lycopene, as well as ascorbic acid. Whereas when we use ozone for washing of tomatoes, we do not achieve 5 log reduction. We do receive 1 or 2 or 3 log, maximum 1 or 2 log reductions, but we do not see any changes in ascorbic acid and lycopene content. It's just because the way that particular compound is present in a matrix. So if you remember, I showed you the very similar image when we were going through the plasma. Same thing, as I said, it's applicable whether it's a plasma system or with the ozone system. And another interesting application when it comes to ozone or gaseous ozone is is one of those Japanese application. For example, there is a processing unit, which is cheese manufacturing unit. It's a chamber of like cheese cutting chamber. Once cheese is taken out of vessel, it is cut in a room and then it is packed. And while cutting, when the shift is over, that particular room may contain some of those microorganisms. So that particular room is cleaned with the sodium hypochlorite, even the cutting surfaces and even the floor is cleaned. But some of the microorganisms, although foodborne microorganisms are not airborne, so they're not transmitted airborne, but they are present in air in a form of droplets or in a form of dust and other things. So think if that particular whole room itself is fumigated with ozone, as it's seen here for storage of food stuff, is fumigated with the room for an hour or two, and it will completely decontaminate the whole room. And same thing can be done also for normal refrigerator or refrigerated storage or cold storage systems. And then it helps in controlling or reducing the cross contamination. So these are some of the way how best it can be used. And the experiment which I was showing you with the bread and a plasma gases, similar experiments were also carried out with ozone. And the obvious reason is at the moment why we have a limited application for ozone in our lab is because we came up with the new regulations that we cannot keep the oxygen cylinders or any of those compressed gases inside a lab. It has to be controlled from outside. And then moreover, most of these investigations are now, we investigate only based on the industrial requirements. So some other application, if you look into here, now this is quite old example. I don't know the existence of this company at this stage. It was again, for instance, raw potatoes, cleaned, dry brushing in ozone gas with 100% relative humidity, UV exposed, that is Venta fresh, disinfection tunnel, the storage of gaseous ozone, ozone washing, UV bath system, ozone, UV tunnel, electrolyzed water bath. And this is one of the simple, not simple, complicated disinfection system which was used for potatoes. So, and why it is having too many steps, I'm not, to be honest, very sure why they have used all different types of system, but this is the way which has been communicated by a company who was using ozone for washing of potatoes. And the multiple steps are there just because to avoid any of those microorganisms coming into play. Now, this is the start of our own plasma system. As you can see, this is very, very crude system, which was obviously this wires were wrapped over a cardboard. And then this was the power, black color is the power source as voltage discharge. And then we were able to see this type of blue light because of plasma generation. And that was the beginning of how we started moving from ozone to generate that particular ozone or reactive species within a packet. These were first early experiments, and this is just design drawn, and we found it very effective. And then based on that, we moved forward, started the collaboration with the engineers who are much more familiar with electrical systems. And now you have seen a lot of plasma systems are available in market. So this is the way start of plasma in plasma systems. And then coming back to other applications, and as far as grain is concerned, and again, if you remember, I showed you this particular structure when we use it for plasma. And this is basically an oxygreen process as a French patented process where they use ozone in a grain silo. And there's also outlet or residual ozone destruction unit. That means it's made up of activated carbon. Whatever excess ozone is, it will goes in here, and it will just convert back to oxygen. And this is quite interesting in one way because when we store grains in silos, we always aerate it just to avoid the buildup of CO2 due to insect infestation, leading to mold growth and causing further damage to grain. Whereas when we transfer ozone through it, we are able to solve that particular problem. So what are the benefits of using ozone food grain industry? Obviously, because of Montreal Protocol, they banned certain pesticides which can deplete the ozone layer in troposphere. Concerns with insect resistance and consumer demand for chemical-free grains and persistent use of chemicals were not only reported to have environmental or social effect, health concern, but also antimicrobial resistance. So hence, so ozone is the cleanest one, which is obviously green, generally recognized as safe gas chemical, but also does not leave any residue. Now, when it comes to microtoxins, so if you look at this particular specific mechanism for degradation of deoxynivalenol and similar for aflatoxin or so, the core mechanism here is mainly ozone attacks on double bonds. You know, it only attacks on a double bond of on C double bond O, forming ozonoid, and then it disintegrate, make it more or less toxic. So this is a particular microtoxin with ozone attacking the double bond, forming a monozoid, and this monozoid, it opens up a ring and then it becomes less toxic or becomes completely useless aflatoxin. So this is one of the way how ozone will work on a specific microtoxin. Similar thing can be with aflatoxin. What these reactions are not exactly as what is being proposed here. This is a hypothetical one, but that's the main mechanism how ozone degrades, is by attacking on C double bond C. In a similar fashion, it also degrades anthocyanins or other bioactive compounds. Now, some of the new applications, what's being looked into as far as food grain is concerned. Normally, if you look at baking process or bread baking process, we have a wheat flour. Normally, chlorine is used as an antimicrobial agent. Ingredients are mixed with various preservatives, and then dough is prepared, fermentation, and you get a bread with a lot of chemical residues because you're using a lot of different chemicals. And some of the preservatives, which are like benzoyl peroxide, bromates, are no longer permitted in the EU and some of the countries as well. But in certain countries, they're still allowed to be used. Whereas, think if we use ozone with washing of the wheat, so use it as an antimicrobial agent, or to use ozone in dough stage. That means the blades of Hobart mixer to make a dough, it's having a lot of different holes and ozone is injected, and which is used while making a dough before adding into the yeast or different fermentation step. It does some good things, that is act as antimicrobial agent, supplies oxygen, which is good because ozone goes back to its oxygen. Ozone converts back to oxygen, and you can have a bread with no chemical residue. So this was one of the projects which we were part of along with our French colleagues on Ozone Bake. That means using ozone across the bakery line, and also to use ozone on disinfection of the places for cleaning of the surfaces where ozone is used for. Where ozone is used for decontamination of the surfaces where breads are cut. So this was the example where it can be used for food grain product applications. This is one of the old application for a lot of places. Meat is consumed as in the form of sausages, and sausage natural casing is again ozonated, like ozonated water, which goes into the casing, and casing is washed by using ozone containing water, so that we can decontaminate the casing prior to filling in the minced meat for food purposes. So this is another application for sausages. Another application here for meat processing. This is again microbial count on a chicken stored under normal and ozone-rich environment. And to be honest, this was the study which made us to think we can use plasma-rich air for making a cold storage room, what I was showing you this morning and yesterday about the chamber which was built exclusively for plasma air. So microorganism, as you can see, normal storage and ozone atmosphere, we can see that significant decrease in different types of bacteria, E. coli, Salmonella, coliform, psychotropes, and viable aerobes. So that means ozone-rich environment, it is not doing anything with the chicken, but it is clearing of the air where this particular chicken is stored. It is very similar to aseptic processing. If you remember undergrad food processing courses where we have aseptically processed juice packed in aseptic condition will have a better shelf life compared to normal processes. So this is making aseptic conditions by using specific chemicals. And similarly, going back to another application of similar type of Venta Fresh that was related to frozen meat, and it was very simple because most of the frozen meat, when they are frozen meat or any of the frozen food, when they are defrosted overnight at either at a room temperature or at 4 degrees, that much time is sufficient enough for microorganisms which are under hibernation during frozen condition, because the freezing does not kill microorganisms, but they restrict their growth. But when they're thawed, when their thawing is taking place or defrosting is taking place, these microorganisms can grow, and then they can continue to grow and then can have spoiled end product. So if this thawing or defrosting is carried out in ozone containing water, then we are able to eliminate that microorganism during defrosting or during thawing. So this is another application how and where ozone can be used. And any of those experiments related to this can be planned to prove this point. Now this is the setup what I showed you the earlier bubble column reactor, and this is look much more fancier and neater diagram to show how it experimental setup it was made to measure the pH, temperature, ozone measurements, and excess ozone goes to ozone destructor. This was the experimental setup for liquid food application, whether it's water, fruit juices, or any other liquid food. Now, if you look into the mechanism of ozone, this is very similar again to the plasma. Only difference is here, since we use oxygen, nearly pure oxygen to produce ozone. So all the reactive species what are formed, they are as a result of hydrogen and oxygen, and the reaction of the main mechanism for inactivation is either due to the free radicals of superoxide or peroxide radicals or hydroxyl radical, or as a molecular ozone, as what you have seen in the formation of monozoid for aflatoxins. So when it comes to various factors which influences efficacy of ozone, A is a flow rate. Higher the flow rate, less of the ozone will be produced, but bubble size will be bigger. Whereas if it's slower the flow rate, will have higher ozone concentration, but bubble size will be really small, so which may form a channel and escape the treatment chamber. So it has to be an optimum flow rate. Second one is ozone concentration. And when we are using very nearly 100% or 99% pure ozone or oxygen, so maximum conversion of oxygen to ozone is only around 13% or 8 to 9%. That means 100% oxygen cannot be converted into 100% ozone. The maximum efficacy is only up to 7%, 8% in some system. I have seen the companies that are claiming up to 13% conversion rates. But the system what we have been working on was maximum around 8% weight by weight conversion of oxygen to ozone. So oxygen component is always there when ozone is supplied to a food product. Second factor is again the temperature. At low temperature, ozone is having a longer half-life compared to at elevated temperature. So that's why it's another reason why it is also classified as non-thermal technology, because it achieves 5-log reduction at sublethal temperature. pH again plays a very important role. If we have a lower pH, we have a better inactivation efficacies. This is because of your hurdle approach. Humidity, again, as you've seen in the previous slide, presence of humidity helps in formation of more of the free radicals. OH, another one. That's another positive side of it. Bubble size, that is largely dependent on the flow rate. I already mentioned smaller, medium, or large scale bubbles. Larger scale bubble have a less mass transfer. The smaller bubbles have a larger mass transfer, but they have a channelizing effect. Other one is organic matter content, how much organic matter is present in. If you take model food solution like distilled water or saline solution, we can get 5-log reduction in less than a minute. Whereas when we take unfiltered juice, it can take up to 10 to 15 minutes. And if you take a milk, it will take a bit longer. And if it's having oil in it, it will take even much longer to achieve desired microbial reduction. So that's organic matter is critical over here. Now, some other way of improving the applications are here to have micro bubbles of ozone. So if you have tiny bubbles of ozone, that means that either to use high pressure jets, which are normally used also for cleaning of cars, that means having high pressure jets, so that they can make either nano bubbles or micro bubbles to improve the efficacy, or to use ultrasonics to have advanced oxidation processes. So these are again the combination how best it can be used. And apart from food application of ozone, the other types of applications are also for using aquaculture, cooling towers, pharmaceuticals, pulp and paper industry, gaseous sterilization, cleaning and disinfection of healthcare textiles. Now, this particular application of cleaning and disinfection of healthcare textiles, this was very, very interesting application which I came across whilst I was in Japan, where a washing machine was made based on ozone. And this was presented by the Rip G. Rice. Unfortunately, he was the main man who was responsible for getting GRAS status for ozone. He passed away 3 years ago, and at the age of 98, he got involved in this book at the age of 90 with us. And he's the one, whole of his life, he worked on ozone, worked with the ozone, and he had his own consultancy. And he was the pioneer man to bring in almost all the application of ozone. And he always believed if we translate every of the Japanese document into English, we have a huge number of applications. So this particular book was mainly, one of the driving force was Rip G. Rice. And he was the one who was showing this particular washing machine. Now, if you look into the normal washing process, we have clothes goes in a washing machine, it rinses with the water, soaks it, then you have a detergent. Detergent contains anti-oxidizing agent which oxidizes the dirt, whether you talk about Ariel and all different brands, they say use of enzyme and different stains removal or whatever, it oxidizes it, and then to second wash you need it to remove the detergent, and then you get cleaned clothes. But when it comes to ozone, you have a water in, you have water into a chamber, and then you have ozone which is injected into the water, and that acts as an oxidizing agent to clean the clothes or any of those textile material. Now, the obvious question will be, since ozone is very having much better oxidizing capabilities. I was about to say 3,000 times because that's not that's very arbitrary figure. But it's much more oxidizing power compared to chlorine or quaternary ammonium compound, which are also used as in a detergent different formulation. So it will bleach the colors. Yes, it can, because every washing with any detergent will also bleach the color over the time. But here we're talking about food services, which are mainly white lab coats or healthcare. For instance, if somebody is working in the hospital industry and they have a lot of blood stains and everything, before that healthcare or in clinical settings, those clothes are discarded. They have to be disinfected or they have to be decontaminated. One is either they are autoclaved or such type of technology is much more useful for such sectors where color is not an issue, or we have to discard it before it is disposed for whatever reason. So this is one of the interesting applications, how we can see how we can use oxidizing power of ozone in laundry industry. So this was the most interesting application which I did see while this ozone was presented in. So still we have some bit of time, and do you have any questions so far related to ozone and some of the technique before I move on to the UV LED light? So I do not see any such question now. So anyway, I'll move on to the UV light, and maybe in 5 to 10 minutes, we just start with this and we'll continue maybe after the break. So now, what is basically UV light? I'm not going to go again into the basics or fundamentals of UV light or creation of UV light, because this is very well investigated and very well studied. Whereas when it comes to UV light, so the applications related to UV are all anything between wavelength less than 400 will be considered as UV light. So UV light applications are for food surface decontamination, especially food processing equipment, pasteurization of food juices, lethal treatment on the surface of meats, and all this can improve shelf life extension. And it does not form any of those hazardous byproducts, and is completely non-thermal, versatile, and one of the cost-effective technique. The only reason over here when it comes to UV light is the creation of UV light by using either by using a lamp, mercury lamp, or different system which is a concern. Now the system has moved from UV to LED light system, that is light emitting diode. The reason behind that is because most of the UV light is supposed to be exposed a food surface with the band of UV light from 200 to 400, because 100 nanometer itself is oxidized within an air, doesn't fall onto a surface. So if 253 nanometer is effective against a microbial inactivation, there is no point in exposing the whole surface with a band of UV light, which may lead to further oxidation. So that's was the basis of advancing UV light in terms of LED light. And if you look at this particular simple LED light, which is obviously having P and N type layer and negative contact and positive contact, and now their precise LED lights are available, which are much more sustainable, robust, and have a practical use in the food industry, so that we can target a specific wavelength, or we can target a band of specific wavelength between 253 to 285, or between 300 to 365, depending upon application what we need. And when it comes to UV light inactivation mechanism, this is again an indirect one, which is the formation of reactive species, but with certain wavelength, we did not see the formation of these reactive species. Whereas what is very well established, whether it's UV LED light or UV light, is for DNA base pairing. That means because of H mu, that is UV light, it causes degradation of DNA. Now I'll just quickly show you one of the most interesting applications. This is one of our PhD student here. And then, okay, before I turn this video, have a look at this particular system. This is the system which was designed along with Tyndall Institute, that is on photonics. These LED light systems were configured in something like this, with 285, 365, and 405 wavelength covering UV A, B, and C. And these were 3 in series, having a maximum current, whatever is written, 30 milliamps or 1 amps. and maximum voltage, and these were configured A, B, C, BCA, CBA. So that means this was injected having 3 different channels, so that we can use 2 frequencies, 2 wavelengths together, or 1 wavelength together, and based on that, based on that, we can treat the samples with LED light system. And then this became the basis of developing another system, which a particular company converted into handheld, is having a handheld system to decontaminate any surface. And due to COVID, they have very good business at the moment to have fast track system for using handheld. So obviously, as you can see, the lab practice, and I just asked him to send me the video of the handheld LED system. So it is basically all the safety things are required before we use any technology. And even entering into a lab, it is very important to have all those gears which are different for different people. So forget about the eating in the lab. Now this is a handheld system, as you can see clearly. Now, if you see, this is handheld system, and the distance plays an important role. And by doing so, within less than 20 seconds or 30 seconds, you're able to achieve 5 log reductions for any given microorganism. It is nothing, it's just an LED light, and it can have number of different practical applications. And this particular equipment just came in for testing to decontaminate the surfaces. As you can see, even if it is used for won't say the domestic application at the moment, but if it is even used in food industry to decontaminate surfaces, or some of the application what we're looking for such type of equipment in healthcare industry, especially to sterilize the forceps and all, which is used in dentistry as well as by other clinical settings, so that you don't have to dip every time into alcohol, or you have to put it into autoclave to make it much more sustainable use, not only for food sector, but for other sectors as well. So this was the basis of designing the system where we control different wavelengths. And I'll just show you some of the data related to that. And before going for that, it was just the measurement was also carried out how much UV light we are putting in. One is to measure UV intensity by using a simple power meter, which is easily available, or we also use econometry. This is econometry is a chemical way of measuring amount of UV light going in, and or by using a specific sensor system. And there is no point in going into details of this method, that means how it is operated, but this is very straightforward method based on this particular compound, and then how much it is oxidized to determine what is the energy coming out of those wavelength. Because by using different power meter, it does give ultrasound, it does give UV intensity, watt per centimeter square, but this is not the best way of measuring the power, given power. But all these measurement was done as an academic exercise to see what are differences in measurement of power. Now, another attribute was whether it heats up sample. But if you look at the thermal image of the sample before UV treatment and after UV treatment, even for continuous exposure for 10 minutes at different wavelength, we did not see any increase more than 2 degrees. As you can see here, it's 18.7 degrees Celsius, and whereas this temperature is around 16. So mainly on 1 or 2 or 3 degrees Celsius temperature increase happens. So that means it's completely non-thermal. And 10 minutes treatment time is way too much for such type of system. So what was done was, again, with the with the changes in the temperature, with alone, control alone, with 365, 285, 405 wavelength, or combination of these wavelength. So this was the system which was designed. And then if you look at the optical power distribution across the treatment plane, 1 centimeter, 3 centimeter, and 5 centimeter, that is distance between the UV LED light and the surface. And these were the wavelength spectra. That means when it says 285 nanometer, it is not exactly 285, it is between plus and minus 3 wavelengths. And these are the LED light which were supplied by a manufacturer from the US on radionics, and then it was configured onto a simple plate system, and then this particular system was evaluated and then measured the power center left, right, up and down. You can see there's significant variation in the power level for different power level, and then it was treated and different power level was measured before going for actual treatment. So so what we'll do is, when we can come back, and I'll continue with this this particular LED light system. Maybe we'll see on remotely, maybe at 2 o'clock. Let's see. Yeah, we'll may come back at 2 o'clock so that we can continue further with this. Or well, I'll pass it on to the organizer and she can have a proper clarity on the time. So over to you.